Hello, everyone. In this work, we present SIAM, Synchronous Interaction Attention for Human Mesh Recovery. This project was supported by the CVIS lab at Toronto Metropolitan University. First, let's understand what human mesh recovery is. Human mesh recovery is the task of estimating a 3D human body model, like SMPL, directly from RGB images. In simple terms, we take a regular image and predict a full 3D body shape and pose from it. As a core problem in computer vision, it has seen major progress over the past few years. Many innovative methods have been proposed, especially to improve performance in challenging situations like ambiguity and occlusion. Despite major progress in human mesh recovery, current methods still struggle to produce accurate meshes during dynamic actions or when there are ambiguities and occlusions between people and objects. However, as humans, we can naturally infer plausible 3D pose and shape even in those challenging situations. To address this, we propose a synchronous interaction attention framework that explicitly models spatial relationships between multiple people in a scene. In addition, we introduce a feature decomposition strategy that separates shared scene information and extracts richer, instance-specific features for more accurate mesh recovery. Here's an overview of our method. We start with a high-resolution backbone that extracts detailed instance-level features from synchronized video frames. From there, the model predicts SMPL shape and pose parameters for each person while explicitly modeling interactions across both space and time. First, we extract frame-wise features using the high-resolution backbone. Instead of treating each frame or each person independently, we pass these features into our SIAM module, which builds a spatio-temporal interaction graph. In this graph, every detected person is represented as a node, allowing the model to reason about relationships both within the same frame and across neighboring frames. The SIAM module applies self-attention to these instance-level features. It projects them into query, key, and value representations, and computes an attention matrix that captures how strongly each person relates to others throughout the sequence. This allows each person's representation to be refined using contextual information from nearby individuals in space and time. After that, an FD step disentangles these interaction-aware features into instance-specific representations. By modeling cross-frame relationships, the system improves temporal consistency, handles occlusions and motion blur more effectively, and better captures group dynamics. To better capture interactions between multiple people, we use a self-attention mechanism in our SIA module. Unlike standard self-attention used for single images, our approach is designed for video. It models relationships between different people across synchronized frames. Instead of focusing only on spatial information, it also integrates features over time, allowing the model to better understand coordinated motion, handle occlusions, and maintain temporal consistency. Here, we compare the real-time performance of SIAM with state-of-the-art models in terms of inference time and mean vertex error. As shown in the figure, SIAM achieves both the lowest mean vertex error and the fastest inference speed, running at 40 milliseconds per frame, which is about 24 frames per second at a resolution of 450. Here, you can see SIAM running in real time. The FPS varies depending on the resolution of the input video, with higher resolutions slightly affecting performance. This slide compares our method with the Eschgari model. The errors from Eschgari are highlighted in red, while the correct estimations from SIAM are shown in green. On the right side, you can see the ground truth alongside SIAM's predictions, with the numerical errors clearly indicated. Table 1 clearly shows that our SIA and FD modules improve performance in both frame-based and video-based settings, using two backbones, HRNet 32 and HRNet 48. With HRNet 32, The full model, combining both SIA and FD, achieves the lowest errors in the frame-based setting. In the video-based setting, the best results are again obtained when both modules are used, highlighting the model's strength in handling temporal information. When we switch to HRNet48, we observe the same trend. The configuration with both SIA and FD consistently performs the best. In the video-based setting, the performance improves even further, reaching a 14.5% gain. Table 2 shows the qualitative results on the CMU Panoptic dataset across 4 different activities, with the average performance reported in the last column. Table 3 presents the qualitative results on the Agora test set. As you can see, our posed model achieves the lowest joint and vertex errors, along with the highest F1 score. Thanks for your interest in our work. You can check out our website for more details.